Hello and welcome. In this video, we're going to take a look at the substitution rule for integrals, but this time we're going to be taking a look at the case where we have a definite integral. And how do you tackle changing the variable from, say, x to u, or some new variable that makes it easier to integrate, when you also have an interval that was given for the original variable? So let's take a look and remember how we actually use the substitution rule in the first place. Well, a substitution rule is where we pick a new variable like u to represent a function of the given variable like g of x. And if that's differentiable, and let's say that this inner function g of x has the range I, and our outside function f is continuous on that interval I, then what we'll do is we'll take a look at the derivative of u, or that's g prime. We'll rearrange that into differential form so that we get du equals g prime of x dx. And if we're given the function f of g of x multiplied by g prime of x dx to integrate here, then we'll be able to make the two substitutions, replace the inside function with u, replace this factor of g prime x and dx with this new integrating variable u. So we just end up with f of u du. So let me take away a lot of the words here and just look at the main pieces. All right, so really the parts here that we're calculating, we have to choose a value u equal g of x, and then we also have to look at the derivative of that and try to match that up with the given integral so that you can see that we're going to be able to replace g of x with u, and we'll hopefully get rid of everything else in other factors here involving x so that we end up with an integral that's simply in terms of u. And what we're going to be changing here now is, of course, we're going to make this a definite integral. Say that we want to integrate from x equals a to x equals b. Well, if we were to not worry about changing the variable, then the antiderivative of this would be some antiderivative of f, let's call it capital F, at g of x. Of course, you can check that with the chain rule. If you were to take the derivative of this, the derivative of capital F would be little f, evaluated at the inside function, and then multiplied by the derivative of the inside. And then we would evaluate this from a to b. No problem. Now remember, when we write this notation with the vertical bar AB, that just means we're plugging in x equals A and x equals B. And if it's ever not clear, you could always make extra room here and even write that in, x equals A to x equals B. That can be really useful in multivariable calculus when we actually have several variables all at one go. Now, if you've changed the variable to f of u, then let's say, again, capital F is an antiderivative. Maybe we'll write that off the side here. F prime of x equals little f of x. And x is just a variable, so it doesn't even matter. F prime of u would still then, of course, just equal f of u. Well, by changing the variable to u now, the antiderivative would be capital F of u, and then we would evaluate that as well. But we can't evaluate that at x equals a and x equals b because our variable is u now at this point in time. So that's where we're going to make this a little extra step here. Is we want to change the interval to match this new variable. How are we going to do that? Well, when x equals a, since u is equal to g of x, the u value when x equals a is simply g of a. So why don't we make that c? Same thing with b. We'll call that d, where c is equal to g of a, and d is equal to g of b. So now we're going to be making the substitutions using u equals c and u equals d. So in one case, by not changing the variable from x to u at all, well, we would evaluate in final f evaluated at g of b minus f evaluated at g of a. Whereas if we just change the variable to u and leave it that way, we end up with capital F evaluated at d minus capital F evaluated at c. Okay, so this gives us really a couple options to get to the correct answer at the end, and they are equivalent answers. What we tend to do with indefinite integrals is we evaluate the integral by changing the variable to u, getting the antiderivative, and then plugging back in g of x. And that would be fine because then we'll plug in a and b and we'll get our answer. You can see the process of steps that we have to do there. But what we can do with definite integrals is follow the same process. We'll evaluate the integral by changing the variable, but we'll also include this extra step of changing the interval. And then we'll find the antiderivative in terms of u, and we'll just plug in c and d. It's just as many steps, basically. In either process, we're going to be changing the variable and finding an antiderivative. It's up to you if you want to change the variable back to x and then plug in a and b, or change your interval first and simply plug c and d into the new antiderivative. This is probably the way I'm going to recommend, is following this nice straightforward process of changing the variable but not changing back again. You just have to remember to change the interval. Now, the reason why I suggest that method is when we change the variable to u, if you continue to write the original interval, then it doesn't make sense anymore. If you change the interval from x to u, but you still have the bounds on your integral symbol as the original bounds for x, that's not going to be obvious. When somebody reads your work, they're going to see that a and the b and just assume that those are the interval boundaries for u. So if you really, really insist on changing the variable to u, finding an antiderivative, and working your back again, plugging back in x, then what you'll have to do is treat it as an indefinite integral. Don't write your a's and b's on there. Don't write the bounds. Simply just treat it as an indefinite integral. Find the antiderivative. Don't worry about the plus c, that constant of integration, and then plug in your b and a. But the moment that you write down a change of variables with du, but you still have the initial boundaries for x on your integral, then you're confusing somebody. Somebody who's reading your work would just assume that the a and the b are the boundaries on u. That's why I recommend just leave it as a definite integral, change the boundaries as you go. It's not any extra work, it's just this thing you have to do earlier on in the process instead of extra work at the end. So let's try a couple examples so you see this extra step included at the beginning instead of changing the variable at the end. Well, in this example, we're going to take a look at the definite integral of 2x times the square root of 3x squared plus 4 from x equals 0 to x equals 2. Now let's take a look and try to find that inside function. See here, of course, inside the square root, we have a function of x, and the derivative of that inner function, 3x squared plus 4, well, that's going to get us 6x. Well, that's kind of convenient since we have a 2x on the outside here. So it looks like it's going to be a good substitution to use. U equals 3x squared plus 4. Now remember to take the derivative of that and write it in differential form. Now it's good to make the comparison here with what we have in the integral. We have 2x dx, and du is equal to 6x dx, and so it's very close. What can be really easy to do is just to rearrange this differential form of the derivative so that we can get dx equals du divided by the derivative of u. And then we can simply make two substitutions, and if everything works out, all of the x's will be canceled out of the integral, so we end up with an integral in terms of u. But because we're changing the variable to u, we have to remember these boundaries. 0 and 2 are the boundaries of the interval of x. Think about it this way. We've got the x-axis right now, and we are integrating from 0 to 2. The new horizontal axis is actually going to be the u-axis. And because we're doing a transformation on x, 3x squared plus 4, well, you have to think about taking the endpoints, 0 and 2, squaring those, multiplying them by 3, so that can make our interval get quite wide, and then shifting it by 4. So if we plug 0 into u is equal to 3 times 0 squared plus 4. And so that's just going to end up being 4 now. And we'll have to also plug 2 into u, 3 times 2 squared plus 4, and that's going to get us 16. Now, it is entirely possible that through some sort of transformations of a and b, we end up with a new interval where a has suddenly gotten to be much larger, and b, when we plug that in, ends up being a smaller value. And it's going to be a little bit weird because then we're going to be integrating with an integral with a large number on the bottom and a smaller number on the top. Now that might bother you, but don't worry, it's still going to be interpreted correctly. It will still end up with a valid answer. And if it really does sort of bother you enough that you end up with a bigger number and a smaller number on the top, remember that you can change the order of the interval by slapping a minus sign on the front. It's just the direction in which we are integrating. So we can always fix that if you don't like that idea. Well, here, I just need to rewrite the integral. From 0 to 2 is now going to be changing to the interval for u from 4 to 16. And I'm going to leave this 2x because I'm not substituting anything in there, but I will change my 3x squared plus 4 to simply just be u, and my dx is going to end up being du over 6x. And that is going to ensure that the x's are removed from the integral, making this just 2 over 6, which is 1/3. 1/3 is a constant that can be pulled out front, and then it's simply just a matter of integrating the square root of u, which may be worthwhile to write as u to the 1/2. And now we can simply use the power rule. Now by raising the power by 1, we end up with a power of 3/2, and instead of dividing by 3/2, it's much easier to multiply by 2/3. And so that is going to end up getting us 2/9. Now it's at this point in time that if this was an indefinite integral, we'd be adding our arbitrary constant plus c. We don't need to do that with definite integrals since any antiderivative can be evaluated at the endpoints of our interval. And if this was an indefinite integral, this would also be the time when we would switch our u variable back to x. We don't have to do that. We did that extra work already with changing the variable and the bounds. We don't have to worry about that extra process now. We can simply plug in 16 and 4. And 16 to the 3/2 is the same thing as the square root of 16 cubed. Square rooting 16, we end up with 4, and 4 cubed is then going to end up being 64. And 4 to the 3/2 is the square root of 4 cubed, which is 8. And that leaves us with 112 over 9. Okay, well, let's try one more example. Okay, well, this one might be a little bit more challenging to try to decipher what our substitution should be. But once again, try to think of a function inside of a function. Make sure that when you choose that inside function, hopefully its derivative shows up as a factor somewhere. You may have to visualize this one a little differently. By thinking about fractions, we can always imagine this as a product instead. 3x over 5 minus x squared is the same thing as 3x times 1 over 5 minus x squared. And if we write the integral that way, then you can kind of start to see that, well, this is sort of a function inside of another function. It's the 1 over x function, but we're changing the x to be a function 5 minus x squared. If that's our inside function, the derivative of an x squared or quadratic, it's going to be a linear, and that's going to be probably the right way to go here. So we're going to make the substitution where u equals the denominator. We're going to hope for the best. It's always easy to feel a little bit of uncertainty when you pick this substitution in the first place. You can start to feel a little bit more comfortable when you take a look at the derivative and see that that looks similar to something else that is a factor of your integrand. Make sure to change this to differential form and solve for du. Both of those substitutions will be hopefully able to get rid of all of the x's in our integrand. Now I have to make sure to change the interval of integration. So when x is equal to, let's say, 2, we'll start with the top. U is equal to 5 minus 2 squared, which is equal to 1. And when x is equal to 1, then u is equal to 4. Okay, this is one of those scenarios, like I said, it can happen. We're going to be integrating now from 4 to 1, which is, of course, it does feel pretty backwards. And it looks like things are going to work out for us because x's are eliminated from the integrand. And if there's any constants that don't quite work out perfectly, that's okay. Constant multiples will get moved out to the front. That leaves us with negative 3 over 2 in front of our integral. Well, this is the point where if it bothers you, there's a couple things you could change here. You can write this as 1 over u with du just tucked at the end here, and that's fine. If it bothers you that we're integrating from 4 to 1 instead of 1 to 4, then you can use the fact that we have this negative sign and change this from 1 to 4 and get rid of the negation. Well, why don't we do that? That might just make everybody happy because it's going to also get rid of this negative sign that I don't necessarily want to have there. Okay, well, that's not bad. We hopefully remember what the antiderivative of 1 over u is. Remember, this is where we have absolute values. Since we've already changed the interval of integration, we don't have to make a substitution back. We can simply plug in 4 and 1, and we don't have to worry about the absolute value of 4 or the absolute value of 1 since those are already positive. Well, the natural logarithm of 1 is 0. The natural logarithm of 4 is the same thing as the natural logarithm of 2 squared. And remember, we have a nice little property of logarithms here that we can use by bringing exponents down. That means that the natural logarithm of 2 squared is simply 2 times the natural logarithm of 2. That's going to help us cancel that 2 in front in the denominator, and we'll end up with 3 times the natural logarithm of 2. Well, and there we have it. If we have a definite integral and we have to apply the substitution method, then as you change the variable of integration, then you should probably be changing the interval along with it. It is valid just to treat it as an indefinite integral, change the variable back to the original, and then solve the definite integral. But you end up doing just about as much work anyways, and following this process where you do a little bit of extra legwork at the beginning means that you go straight to the answer at the end all in one major process. Now, of course, it's easier said than done. Finding antiderivatives just by using substitution is not always going to work. And there are potential problems. You may even have to use substitution more than once and change the variable again. Of course, you won't be able to use u constantly as your only variable to choose for your inside function. Just make sure that when you change the variable, you're creating something new. So if we go from x to u, and then maybe from u, if you have to do another substitution, change to r, and just keep changing the interval every time you change the symbol you're integrating with. Well, anyway, I hope that helps, and I'll see you in the next video. Thanks for watching.